So we have now done integrals in two-dimensional regions, in rectangular regions, in regions where one or more of the boundaries represents a functional relationship between two of the variables, and in polar coordinates, regions most easily described with polar coordinates. But these are all ultimately flat regions that occur in the xy plane, and our predominant interpretation of these integrals has been in computing volumes of regions that lie above the xy plane, although we've tried to emphasize the fact that integrals are not limited to calculating volumes and can in fact be used to calculate anything which has a density spread over an area. We now want to extend that idea to do integral calculations of density spread over an area when that area is no longer constrained to lie within the xy plane, when in fact that area can occupy a surface in three-dimensional space of arbitrary shape. For instance, you might want to calculate the total amount of paint required to paint an airplane, where the thickness of the paint depends on what part of the plane you are trying to coat. And so this would be a surface integral of the paint thickness over the surface of the airplane. So that is indeed a two-dimensional surface, but it is of course not restricted to the xy plane, and so we would not be able to do it with our current set of tools. So we now want to take just one lesson to define surfaces in a more general way than we have in the past, to prepare ourselves to begin doing integrals on surfaces. But first we're going to take this time to define them in a very general way and very powerful way. So we begin by recalling our results on parametric curves. So we had previously defined vector functions of one variable, r, a position in space, as a function of a parameter t, which is really three equations, an equation for x, an equation for y, and an equation for z, all depending on the parameter t. And we said that this traced out what was called a parametric curve. And because this function has one variable, the object in space was a one-dimensional curve. The only thing we're going to start by doing now is to say, okay, that's fine. R is a position, and if it depends on one variable, you get a curve. What if it depends on two? So let's name those two variables, those two parameters, u and v. This is the convention in many books to call them u and v. And suppose that r, this position function, now depends on these two variables, u and v. So what that means is that x, y, and z now all take two arguments as well. They depend on u and v. What this traces out is called a parametric surface. It's very much like a parametric curve, except that it has two variables. So suppose v were just 0, or v were some constant, held fixed, and we let u vary. Then this would be a parametric function of the one variable u, and that would trace out a curve. But now if v changes a little bit, it will trace out a different curve nearby. And if v changes a little bit more, and we sweep over u, we'll get another slightly different curve. And if we begin connecting these one-dimensional curves, we have one parameter family of one-dimensional curves, and the result is that it traces out a surface. And as it says there on the screen, this is a far more general and powerful way to describe surfaces than you have seen them expressed previously via equations of the form z equals h of x and y. Namely, this way of representing a surface must be single-valued. It can only capture single-valued surfaces, because for every x and y, there is exactly one value returned by the function that is assigned to the coordinate z, and so you are not able to represent with this representation any kind of object that has a top and a bottom surface, such as an airplane, or even simpler things like a sphere. So I'll just give you an example of a parametric surface. Here is a set of equations, a set of parametric equations that depend on two parameters u and v, x u cosine u, y u sine u, and z equal v. And we're going to let u go from 0 to, I should have made that 4 pi, not 2 pi, and v goes from, say, 0 to 2. How in the world could we plot that, and how did I get these pictures that are drawn on the screen? let's take a minute to think about this. So how did we get here? This looks a lot like polar coordinates. X is something cosine u and y is something sine u, and we see that that something is the same in both cases. And so what this looks like is exactly the polar coordinate representation of the coordinates x, y, and z in terms of r and theta, where x is r cosine theta and y is r sine theta, except here r seems to be replaced by u and theta seems to be replaced by u. So here r and theta are both written as u. And so what these two equations tell us, these top two equations, is that in a polar coordinate system, if we think of this in terms of polar coordinates, we have a curve r equals theta. So this u dependence here tells us that r equals theta. For any value of theta, r equals that value of theta. On the other hand, we have z written in terms of the parameter v. It's completely unrelated to x and y because v is unrelated to u. And so z also has various values that lie between 0 and 2. So we have a combination of two things. R and theta are related by the relation r equals theta, and that is this curve right here. It's a spiral that goes around twice because u goes to, as I've said, from 0 to 4 pi, which I should have had written there. So in some sense, this object is going to have this spiral nature in the xy plane. But that's only the u dependence of this surface. This surface also depends on the parameter v. Z equals v, and z stretches between 0 and 2. So it will be a slice of this. It's not a spiral cylinder because it doesn't go off infinitely in both directions, but it would be a slice of a spiral cylinder. It's approximately the shape of a cinnamon roll after you roll it up and slice it into pieces. So here we have vertically the z dependence, the v dependence, and then radially in this spiral direction we have the relationship here with the parameter u, that x and y are related in polar form by the function r equals theta. I want to point out just a couple of things that will help us see the relationship between u and v and this surface that they seem to be generating. So it's very common to draw lines of constant parameter values on the surfaces. Okay, so let's imagine doing that. Let's first draw lines of constant u. If u is constant, then v varies. And that means in our example here that z varies. So if u is held constant, then these lines are going to be vertical in the z direction. And that's what we've drawn here. All the way around this object, we have these lines of constant u. V is varying along each line, and each line corresponds to a different value of u. So this would be u equals 0, working our way to u equals 2 pi, working our way around again to u equals 4 pi, and for each specific value of u, if you let v go between 0 and 2, you trace out one of these blue lines. Similarly, if we imagine holding v constant and letting u vary, then we get these spiral lines. It's just this spiral raised to different levels, z equals v. So this green line would be, say, v equals a half. This could be v equals 1, v equals 3 halves, and so on. These are sometimes called coordinate lines in that they, instead of our nice grid of boxes, lines of constant x and lines of constant y in the xy plane, these lines live on the surface itself, but nevertheless they represent lines of constant coordinate values. Because really on the surface we're still within a two-dimensional coordinate system, uv, which just happens to wind its way through three-dimensional space. So this is an example of parametric surfaces, a very simple example of how we might think about plotting them, and this important idea of coordinate lines, lines of constant u and lines of constant v. There's a couple very simple examples that we can write down equations for that you should already be familiar with. We'll mention these and then we'll show some pictures of some more complicated surfaces. But I said that this is more powerful than simply the graph of a function and more general, and it is true that any surface that can be represented as the graph of a function can also be represented parametrically. So if we have a function z equals some function h of x and y, then we can express this parametrically simply by letting x equal u, y equal v. And since x is u and y is v, then z is just h of u and v. You'll even sometimes just see let x and y themselves be the two parameters. X equals x, y equals y, z equals h of x and y. But I like to put things in terms of u and v just to be consistent so that the calculations are the same every time. It takes a little bit of abstraction at the beginning of the problem to introduce these new variables u and v, but then every calculation that we do works out the same. So for instance, I've drawn here a paraboloid. I should have written that down. Say z equals x squared plus y squared. The lines of constant u and constant v are just the Cartesian coordinate lines projected up onto the surface. So constant u is constant x, and letting y vary, we trace out these paraboloids that are up on the side, these parabolas on the side of the paraboloid, going in the plus and minus y direction because x is held fixed. Similarly, the coordinate lines of constant v correspond to lines of constant y, which are those Cartesian lines projected up on the paraboloid. So we have parabolas in x up on the paraboloid where x varies while y is held constant. So any such surface, any such function, z equals h of x and y, can be represented parametrically. So everything that we're going to learn about parametric surfaces applies equally well to graphs of functions. There's another kind of surface that you saw in Calculus 2 called surfaces of revolution. And the idea is that you take a simple function, a one-dimensional function, y equals f of x, and then we rotate that curve around the x-axis, and that gives us a surface. Really, it even gives us a solid if you want to include all the material inside of that, but we'll be talking about three-dimensional objects in a few lessons. For now, let's focus only on the surface, and this surface can be represented parametrically. To figure out the equations, we recognize that every time we slice in x, so if we pick a value of x and we slice through this surface, then we get a circle of radius f of x at that particular value of x. So if we let x equal some value u, then the radius is f of u. And so why don't we just set x equal to u? Then how do we describe a circle in y and z? So I've tried to sketch this in 3 dimensions, and we have a circle in y and z. We know that the parametric equations for a circle in y and z are y equal r cosine theta and z equal r sine theta. But here the radius is being played by, the role of the radius is being played by the value of the function, which is f of u. So the radius can be f of u, and then v plays the role of a theta variable that goes from 0 to 2 pi. And so these equations right here describe a circle around the x-axis of radius f of u, while this equation here places that at the coordinate value x equals u. Again, we can draw lines of constant u and constant v. Lines of constant u are the object at a fixed value of u. We just said that was a circle. And so I haven't drawn it very well, but here we have circles. At every slice in x, we have a blue circle represent lines of constant u along which v, playing the role of theta, is varying. Meanwhile, the lines of constant v are basically picking an angle through this circle and then sketching this function f as a distance away from the x origin. So all of these curves of constant v look like the function f of u, except rotated by various degrees around the x-axis. Now I'll show you just some more complicated parametric surfaces, just kind of for show and tell, but to give you an idea of why these things are so powerful, the kinds of things that you can do. I would like to have gotten these in better order first, but here, first of all, I have tried to plot the equation for a sphere, z equals the square root of 4 minus x squared minus y squared, a sphere of radius 2. And I've had to plot both the positive and the negative square root of that function in Cartesian coordinates, and you can see that it gives me problems. It gives me problems, first of all, because I had to separate the positive and negative square roots to get the value of z. I have further problems because I have here a square grid from -2 to 2, or maybe -2.5 to 2.5, or something like that. And for many values on that grid, the function is not defined. When x and y are both 2, 4 minus 4 minus 4 is -4, and the square root of -4 does not exist. So there is no value of the function for parts of our grid, and there are places right around the edge of the sphere where, say, 3 of the points have a value and the 4th point does not, and so you get these holes and these jagged edges in the graph of the function. So this is not optimal. In contrast, here's a nice picture of a sphere. No holes, no jagged edges, no problems whatsoever, and I've plotted it parametrically using spherical coordinates, which we'll see in a future section. But here I have nicely on my surface my coordinate lines of constant u are from one pole to the other. V is a coordinate that goes from the North Pole to the South Pole, and u is a coordinate that goes around the equator and lines of latitude. So lines of constant u are these vertical lines, and lines of constant v are these latitude lines. More examples. Here is that thing that I sketched for you a few slides ago. U cosine u, u sine u, so that's like r equals theta, where z equals v. So we get a spiral and then extended upward in the z direction. Let me just get these out of the way here. This is a similar function, similar structure, cosine, sine, u's, and v's. But here we have v cosine u, v sine u, and z equals u. So this is like saying that z equals u, and theta is also being played by u. So this is like saying z equals theta, where r is independent and goes from some minimum value to some maximum value. So z equals theta actually gives us a spiral ramp that looks like this. This parametric surface obviously is double valued, and if I had included more windings, I would have as many values as I wanted, so no way can we express this using graph of a function. Another very similar, cosine, sine, u's and v's, but here we have z equals v, and r looks like it's equaling v. So this is like saying z equals r, or r equals z. The higher up I go, the larger is the radius of my circle. And u is an additional parameter that just goes from 0 to 2 pi, and so it wraps itself around. So 3 very similar equations give me a spiral ramp, a cone, and that cinnamon roll-like spiral object, all done using parametric surfaces. And finally, one of my favorites, this is the parametric equations for technically a torus, more familiarly a donut. I won't go into deriving these equations, it's somewhat lengthy, but I just wanted you to see that we can plot very interesting objects and even complicated objects using these parametric equations. Now, a little bit of calculation. This isn't all show and tell. What things might we like to calculate? And we will calculate tangents, normals, and tangent planes, the same kind of objects that we calculated for graphs of functions, but they will be more useful now in this more powerful setting. So we've already seen how to calculate the tangent plane for the graph of a function, and the method of doing this is very similar for parametric surfaces. So I have my function r of u and v, my position vector r is a function of u and v. And just like for the graph of a function, dh dx and dy dx allowed us to calculate vectors, tangent vectors. They allowed us to calculate slopes, which allowed us to build tangent vectors. When we take the derivatives of our position function with u and v, we also get tangent vectors, except we don't even have to build them. They just naturally give us tangent vectors. So consider dr du. It's the limit as delta u approaches 0 of r u plus delta u minus r of u for some fixed v divided by delta u. What are those objects? If I have here a point r of u and v, if I change u by a small amount, I get some other point, and the difference between those points is a vector in this direction. That is a secant vector. If I now reduce the size of delta u, sorry, I'm using the wrong one. I get another vector, and as I continue reducing the size, I get a vector that is in fact tangent to the surface. That should have been here. Similarly for delta v, as I begin introducing the definition of the partial derivative is the limit as delta v goes to 0, r of u v plus delta v minus r of u v divided by delta v. And as delta v gets smaller and smaller, I get secant vectors, which are more and more closely related to the tangent vector. And so ultimately, both dr du and dr dv are tangent vectors to a surface. We already saw that a surface, a two-dimensional surface, naturally has two tangent vectors, and here we have two such tangent vectors. They both lie in the tangent plane, since they are both tangent to the surface. And so we should immediately be thinking, how can I construct a plane if I know two vectors which lie within it? I can take the cross product of those two vectors and get a third vector which is normal to either one of them, and therefore normal to the tangent plane. So I calculate dr du cross dr dv. That gives me a normal vector n. And as long as n is not equal to 0, then we can find a tangent plane. If n equals 0, that likely indicates a corner, just like if dr ds equaled 0, then we likely had a cusp in a one-dimensional curve. We require also dr du and dr dv, their cross product, not to be 0 to ensure that we don't have some kind of corner on our surface. But as long as that is not 0, then we can calculate two things. We can calculate a unit normal vector, which is often very useful in physics applications, which is just this vector divided by its own magnitude. And for our purposes here today, we can construct the tangent plane. The tangent plane has standard point normal form. It's the set of all points r such that r minus some reference point that's on the surface, the point of tangency, dotted with the normal vector, has to equal 0. This is point normal form of a plane that we've seen in the past. And this allows us to calculate the tangent plane. So the procedure is to first calculate dr du, then dr dv, then the normal vector n, finally take the point at which we are calculating the tangent plane and insert all those things into the equation point normal form for a plane. Last thing in this lesson is one example. So here is a parametric surface. I do not have it plotted, but it is some kind of paraboloid opening out in the y direction. This would be a fun thing for you to put into a piece of graphing software and try to graph this object. I even believe it's a parabolic cylinder. Here's a point on that object. We are asked to find the tangent plane to this surface at this point. So we have our steps. First, we find the normal vector. We calculate dr du, that is 1, 6u, 1. We calculate dr dv, the partial derivative with respect to v, that is 1, 0, negative 1. And then we take the cross product. I have in my head put an I, j, k here and taken the determinant of the resulting pseudo matrix and gotten the normal vector negative 6u, 2, negative 6u. So here we have the normal vector anywhere on the surface for all values of u and v. But we need to know those values of u and v, and the problem does not give them to us directly. It just gives us the x, y, z coordinate, and we need to find u and v. So we have that x, which is u plus v, is 2, y, which is 3u squared, is 3, and z, which is u minus v, is 0. This is a set of equations that we can solve to find u and v. In fact, it's too many equations, and once we find u and v, we have to use the final equation and make sure that the point we were given is actually on the surface. Sometimes the book makes mistakes. So from equation 3, we know that u equals v. That means we can replace v with u, and so 2u equals 2 in equation 1. That means u and v are both 1. Let's go ahead and plug that into equation 2, and we see that indeed that final equation is consistent. So we have found our coordinate point in uv space. It's u equals v equals 1. We're now ready to construct the tangent plane. We plug in u equals 1 to our normal vector, giving us minus 6, 2, minus 6. Our point of tangency is 2, 3, 0, and so the point normal form of the plane, r minus r naught dot n equaling 0, becomes each component of the normal multiplied by the component of r minus r naught. So we have negative 6 times x minus 2. We have 2 times y minus 3, and negative 6 times z minus 0, all adding up to be 0. We can simplify that a little bit more and get the standard form of a plane right here. Note the problem did not ask for it, but as I said, it is very useful in many physical applications to calculate the unit normal. We can do that as well, simply taking that normal vector, negative 6 to negative 6, and dividing by its own magnitude, and we get this result over here.